All right, so last lecture we started working on partial differential equations. And I said that we are not done with ordinary differential equations yet, right? So this class will be continuing to look at partial differential equations, but use what we have learned in ordinary differential equations to explain some of the behaviors we saw at the end of the last lecture, right? And just to remind you what we have seen, we have coded up the solution to this particular partial differential equation. We were looking at du dt plus a times du dx equal to 0. And we have analyzed mathematically, we have basically done the calculus to find the analytical solution to this equation. And particularly when we have periodic boundary conditions, the solution just keeps moving either towards the right if a is greater than 0, or keeps moving towards the left if a is less than 0, without changing the shape, right? So we analytically proved that if we plug in a solution that is u x t equal to any function which is determined by initial condition x minus at, then we know the solution is going to satisfy the differential equation. And if we have periodic condition, then anything moves out of the right boundary is coming back from the left boundary, and anything that moves out if the solution goes towards the left, goes out of the left boundary, comes from the right, right? Okay, and then we derive the finite difference scheme by discretizing only the spatial operator. And the result of the discretization is going to be a set of coupled ordinary differential equations, right? We had three options. We had option 1 is that we are approximating du dx with u of I plus 1 minus ui divided by delta x. So always I'm trying to approximate this at the grid point I. And the second option is if I flip the direction of this approximation, instead of using ui plus 1 and ui, I use ui and ui minus 1, also divided by delta x. And the third option is a more balanced central difference. We are approximating the derivative by looking at the slope between the right neighbor ui plus 1 and the left neighbor ui minus 1. Then I have to divide it by the difference between the two neighbors, which is 2 delta x. Okay. So what have we found in the last lecture? To remind you, let's actually rerun what we've done for the previous lecture. We had the finite difference code, and we can change this line into different forms. So what I have just commented out was the central difference. The left-sided difference would be u minus ul divided by 1 times delta x. That would be a left-biased difference. A right-biased difference would be ur minus u divided by delta x, right? So if we run the, well, I think our option 1 is actually this one. So let's actually put option 1 to test first. ui plus 1 minus ui divided by 2 delta x, right? And we run it, and we want to plot out the solution and the u and at the end. So if we run it, and here our okay, our u is a bunch of names. All right, so basically what this tells me is that when a is equal to 1, which means when the solution is moving towards the right, and I use a right-sided difference, the solution didn't work. All right, and if you want to look at how the solution becomes nan, we can plot x and u to kind of see doesn't work. Let me actually look at how U is going to behave. Right, so that's the initial condition for U, and as U, so let's just plot U for the first 100 steps to see how it works. Basically, we can see that starting from the discontinuity, right? Our initial condition for U, is this. So basically, half of them are 0, half of them are 1. And when we started evolving, we can see that on these two fronts, when 0 changes from 1 and 1 changes back to 0, we start to see wild oscillations, right? So that's how the solution goes unstable. And that can be remedied by switching to the second option. The second option is a left biased finite difference, and after a while we get a solution, although it's not exactly the solution, which we have a periodic solution and we evolved for one period, which means the final solution should be the same as the initial condition. So this is not exactly, the sharp jump has been diffused out into a gentle slope, but still the solution pretty much looks like what it should be, right? And as we can see, if we increase the resolution, for example, to 2000, and we hold on, if we run it, we expect to have a solution which is the red. Now it's a better approximation of the exact solution, right? Exact solution should have an infinitely sharp step as opposed to a slope. So the red one, which is 2000 grid points, is a better approximation to that. All right, and then our third option, the central difference, we can show through Taylor series analysis that it is better approximation to the spatial derivative. Now, if we run this one, again, let's try with 2000 steps. What we see is that, well, the step is actually sharper, but there is a lot of smaller scale oscillations where it should be flat.